So for the elements on the periodic table, it's the first two columns and the last six that are the representative elements. And these are elements whose valence electrons are most clearly understood. That's going to become more and more evident, hopefully, as we go along in this unit and the next one, the one that follows that. I want to start with sublevels, because you're going to find out from the sublevels how that connects to representative elements. Only two sublevels are in the valence level, okay? Those are the S and P sublevel electrons. So we're going to look next then at where the sublevel regions are on the periodic table. Okay. So by region, what we mean is that these are where elements are found whose electrons in the valence level or in those levels immediately preceding or during when we're figuring out the valence level electrons are found. So
what does that word say after who?
whose, should be whose valence level electrons are in these valence level sublevels. Okay? So, or between, we'll just call it this way. This is really not the best way to say it, between the S and P valence levels. So that's not the best way to describe it, but we're really not far enough along for you to understand a deeper definition of it. Okay, this will kind of make sense as we go along. Okay, so we're still going to put our dividing lines in the same place. These are elements whose valence electrons are in these valence levels, sublevels, or between the S and P, I left an E off of valence levels. I know that seems like complex and convoluted, but as we go along, it'll make more sense, okay? I don't have a real clear way of stating what this is until you have an understanding of what the valence level is and what the S and P sublevels are. And we'll get to that. Tomorrow, remember, you're supposed to bring teardrop-shaped balloons, right? One package, at least one package with multiple colors in it. Yes?
Why don't you send out reminders?
I do sometimes, but I'm telling you today, I told you 2 days ago,
Can you send a reminder at like 6?
can I or would I?
Would you and can you?
I will try. Of course I can.
Might as well.
You don't understand the difference between can and would you.
Yeah, I do.
Okay, can means are you capable of? Of course I'm capable of. I've sent other reminds out. So that's not really the right question. Anyway, all right. So we're going to divide it in the same places. Okay? All right? And then this section here is the S sublevel region. Now, there's a reason why I didn't make this S any bigger, because S for sublevels is a lowercase level, lowercase size s, okay? It's not a capital S. So I can't capitalize the first thing in the sentence because it's never supposed to be a capital letter, okay? And then this is called this is the P sublevel region. And then here is the D sublevel region. And the F sublevel region. Now those letters are the first letter of words that describe, well, again, you don't have the information to understand what it is, but describe a certain behavior that occurs when you're doing some exploration of chemicals, okay? Yes?
So we're not supposed to know what this means yet, right?
Not really, no. But it's going to make more sense as we go along. Okay, but you need to know where these are, because when we start writing orbital notation electron configurations, which is kind of the next thing we're going to do, we need to know where these are located, okay? Now, the periodic table is the most important instrument that a chemist has, but it's not perfect. But the reason it's not perfect doesn't have to do with the way that elements behave. It has to do with the way you and I understand things. When we get down on the atomic level, things don't behave the way we're used to them behaving. And I'm trying to explain things as if atoms, or for that matter, subatomic particles, behave the way we're used to baseballs and footballs behaving, but they don't, okay? And so you can't just explain the rules in the way that, it would be nice to be able to explain it. We can't make up the rules, okay? We just have to try to describe as best we can how those things behave based on what you and I understand, all right? This is kind of beyond what we normally understand, so we're trying to understand it as best we can, okay? We're struggling to get there, yes?
Didn't you say the other day that helium was an S level?
What now?
The other day, didn't you say that helium was technically the S
I am
level?
so glad you asked that question, because that's what I'm getting to, okay? So she's asking about helium, and that is exactly why I'm explaining what I just said, because helium doesn't belong here when we're talking about S, P, D, and F sublevels, okay? So helium is here on the periodic table, and it belongs here. It is a noble gas, and all the elements in this last column over here are noble gases. That's where helium belongs, but in terms of S, P, D, and F sublevels, it doesn't have a P sublevel. It doesn't have any electrons in the P sublevel because it doesn't have a P sublevel, period. So helium, when we understand about the arrangement of elements and what the sublevels are and where the electrons go, it actually belongs over here, okay? So let's go on now and talk about regions of major categories of elements, okay? Like where the metals and nonmetals are located. Now, there are a lot of reasons why metals are referred to as metals and their behavior and stuff. But in terms of chemical behavior at the atomic level, metals are atoms that give up electrons to nonmetals. Okay? Metals share electrons with metals in an electron sea, SEA. Nonmetals share electrons with nonmetals and covalent bonds. Now, just a word of warning that I've given you before. When I write these things down, these are general rules. Okay, there are always going to be exceptions. Okay, there are going to be cases where metals will give up electrons to other metals. That just seems kind of strange, but most of the time metals share electrons in a special way. There are times when nonmetals give up electrons to nonmetals, but most of the time they don't. Okay, so this is generally the case for most metals and most nonmetals. Okay, and there are a few cases where metals don't give up electrons to nonmetals. They share the electrons between metals and nonmetals, but it's rare. So we pretty much aren't going to consider that in a high school chemistry class. We want to look at the biggest, greatest, broadest cases. Okay. Now, if you look on your periodic table, you'll see this dark stair-step line. Okay, everybody see that? So that is the dividing line between metals and nonmetals. All right, so we're going to put that stair-step line on this. All right, and we'll label these, okay? We're going to say that these are the metals over here, and that includes this section down here.
You put an extra line.
Did I?
Yes. Good job, Dee.
We don't.
Okay. And we're going to show the nonmetals over here. I did, didn't I? Put an extra line in there. Okay. So around that stair-step line, everywhere except for aluminum, so this is aluminum right here. I would suggest you have your periodic table out and you look at it while we're talking about this. Around that stair-step line, touching the stair-step on two sides except for aluminum, those are called metalloids. Or sometimes they're called semi-metals. Okay? And what that means is that these elements are so close to that dividing line that chemically they sometimes behave like metals and sometimes they behave like nonmetals. So I think I've mentioned this before, but just to be clear, these elements down here along the bottom of the main section of the periodic table that have atomic masses in parentheses, those are man-made elements. And they don't last long enough for us to really know what their behavior is. So for that line to extend down here is, well, you know, we could extend it down there, but we can't really test it to find out because they only last for fractions of a second. So that's why that line wasn't extended down there. Actually, to be fair, also, when I first started building this table in Microsoft Word, in order to be able to add new elements when they discover them, I didn't extend the line down there because the elements were there. So, I mean, I could extend the line, but it doesn't really make sense to do it. We could. I don't know. I have to go back to IUPAC and see if they decide to do that. Remember, IUPAC is the international organization that decides those kind of things, what the name of the elements are, whether they're metals or non-metals, whatever the case is. They're the group that reaches the consensus to decide how to decide all those things. How do we name chemicals? They're the ones that decide all that. Okay. Now this is what you did the homework on. Relative sizes of atoms. Okay. If you did the homework, you already know about the relative sizes of atoms. Okay, that was the point. It's really easy to remember when you do all that because you've done all that work. Yes, they have these places called department stores. I'm sure you can find one. Wait a minute, don't take my rulers. No. We don't have enough for everybody to have one. No. There's not enough for everybody to have one. Put them back. Come on. Come on. I'm not your Brett. Come on. Let's go.
This is a good one too.
Put them back.
We can
What are we
pass them
supposed to
around.
You're not taking my rulers, okay? I'm sorry. I have little 6-inch rulers up there in that little basket right there. If you want to use those little things, you can use those. But I want them back. Just saying.
He gave me protractor.
You can draw your own estimate of it.
What would you like label the like periodic tables? I'd like start this page.
Just periodic table sizes. Part 1 and 2, relative size of atoms. Okay. All right.
Can you go back to the caption?
You're talking about this?
Yeah. The other one. It's the same thing?
Part 1 and part 2.
Alright.
All right.
Wait.
If you want to put notes about what I'm about to talk about on the back of this, you can do that. You can put on separate sheets of paper in your notes or whatever, so you can, as I explain why that happens. Okay? And this may be kind of difficult to grasp, but I'm going to explain what happens in terms of the why they grow bigger and get smaller. Okay? We talked about, in fact, I probably got that illustration where we did that. Let's pull that out. There we go. Remember this illustration?
Oh, Lord.
All right. Electrons have negative charges. That's when we write E negative for the symbol. Like magnets, the north end of a magnet pushes away from the north end of another magnet. Okay? Only the south end is attracted to the north end. All right? So these negative charges, as a rule, want to push apart from each other. You can try this for yourself sometime. You can take and tie a balloon. Let's see, I guess it would work with cotton string. To cotton string. You know how in a really cold, dry day, you can rub it on a wool sweater or a cotton sweater or a polyester sweater, and then it makes your hair stick up if you put it in your hair, right? Well, anyway, some hair. That's because when you rub that balloon on your sweater, it's gathering up electrons from the sweater, okay? And so you got the surface of the balloon with electrons all over it. So those electrons on the first balloon, if you do that with 2 balloons on a string, you put them near each other, they're going to push apart because the electrons push apart from the other electrons. They don't like each other, okay? If some of you may have, I don't know if they still do those demonstrations in physical science, they use pith balls. Y'all see those where you take little balls on a string and see that happen? Okay, you can take 2 pieces of aluminum foil, take little strips out of them, and put them on a piece of wire, and put in any kind of static electric charge, like from a balloon, on one end of the wires. You got to have it insulated. It'll push the little pieces of aluminum apart because you're loading up electrons on there. They push apart. So there's a lot of ways you can demonstrate the fact that electrons push each other apart. The only reason that electrons can be in the same orbital, and we're going to talk about this a lot in orbital notation, the only reason electrons can be in the same orbital is because they have what's called opposite spins. Okay? We don't need to know that right now. What we need to know is this layer of electrons doesn't like this layer of electrons. Okay? And what's really happening is not just the electrons, it's the magnetic electric field, electromagnetic field it's called, around that electron that's pushing apart from other electrons. Okay, all electrons have an electromagnetic field around them. All right, and so these electrons push apart from these right here because of the electromagnetic field. Well, the electromagnetic field creates a kind of a shield as well. So the positively charged protons here, the strength that they should have holding on to these electrons in the second level is reduced because this layer right here is kind of preventing that from happening. It creates an electronic shield. Okay, and this shield this layer here provides another shield to these right here. Okay, so what happens is, if I have just one electron in this level right here, so that'd be 1, 2, 3 electrons, that'd be 3 protons, then the protons have a tough time holding onto that one electron, having to push through this shield, electromagnetic shield provided by the first layer. Okay, so this electron gets kind of spreads out a bit. All right, the size of the atom gets bigger. The electron cloud gets swells because it can't hold on to that one so well because of the shield right here. But the more electrons I put in this level, while at the same time also adding more protons, the more electron power or positive, attracting and negative power there is to pull that level in. So as I add more electrons, I shrink the size of the electron cloud, not increase it. Does that make sense? Huh? Doesn't make sense? Okay. So,
You like explain that one?
do you drive?
Yeah.
Okay. So suppose I send you out to go up and physically pick up your car and move it from one parking place to another. Could you do it? No. But if I take all the guys in here and all the guys from another class and you all go out there with leather gloves on, and you probably could all pick up that car and move it from one parking place to another. I know because I did it. Okay? Not your car. We used to do it for joke. We used to do it as a joke when I was your age, okay? Just because we, yeah. Yeah, we pick up somebody's car and move it into a corner where they couldn't back out, just for fun. Yeah. We didn't have video games back then. Okay. But we always stood around and laughed about it and moved their car out. We never left them stuck there, okay? Anyway, I know that's a sad story to tell. And I'm recording it too. That's terrible.
You're recording it?
Yeah. So anyway, the same thing happens in the next layer. One electron out here, there's a lot of shielding effect from this layer and this layer, keeping the protons from holding on to that one electron out there. But the more electrons I put out there, the more I can shrink it in. Just like the more people I put around your car, the easier it is to pick it up and move it. Okay? You still don't get it?
I mean, kind of. I thought you said that the electrons like push apart from each other. So
They do, but we're talking about protons now holding onto electrons. If protons are positive, the electrons are negative, like the north and south end of a magnet.
Like the more electrons you get, the more protons you get to hold the thing together. Is that what you're saying?
That's kind of the idea.
Okay.
All right, but it has to push its way through that shield to hold on to those electrons. Every time I have a layer of electrons, that's another electromagnetic shield. And so the reason why we have this pattern of elements getting smaller as they go to the right is because we're adding more electrons in that level as we go to the right. And that's called the shielding effect, okay? So the reason this pattern exists is because of the shielding effect. And as we go from one row to the next, we're going to a whole new level. So it gets bigger going down to the next level and smaller going to the right. Okay?
What's it called again?
Shielding effect.
Shield?
Shielding effect. Okay? So the reason this pattern exists is the shielding effect. All right?
Wait, so what does the shield have to do with the size again? Because like I get that like the more protons, the more electrons, like the more protons.
Because each of these layers of electrons create an electromagnetic shield
Yeah.
between the proton and the outermost electrons. It isn't that hard. Just give yourself a chance to digest. Okay? All right? Okay. This is the relative size of atoms. Later on, really in the next unit, we'll find out about how atoms form ions. And I'm not going to spend a lot of time on this, just I'm going to give you kind of a quick introduction to it. Okay, relative size of ions. We're just going to be a quick introduction to this, okay? Not a lot of time spent on it at all. So ions, at least in terms of the monoatomic ions. So let's make a notation. These are monoatomic ions we're talking about. And that won't make sense until we get to 2 or 3 units down the way. But monoatomic ions are formed when atoms either gain electrons or lose electrons. Okay? Monoatomic ions are formed when atoms gain electrons or lose electrons. Remember we said metals tend to give up electrons, nonmetals tend to gain electrons when you're putting them together. That's what we're talking about. Okay? In terms of the relative size, then when we get over here to the nonmetals, we start to, instead of losing electrons on this side, that's what metals do. Metals lose electrons. These over here tend to gain electrons. Okay? So this pattern of smaller and larger also works, but there's a break right here where it starts to, where you got to reset the whole thing. So in this region here, then, we get larger and smaller, larger and smaller. Okay? Because they just get huge right in here. All right? Because we're going from removing electrons to adding electrons, and that just creates a whole new level of instability in that outer level of electrons. Okay? And so the size of the atom just gets huge. You don't have to know so much about why, but the shielding effect is still the reason. Okay? You just got to know this is the general pattern, and it gets, these are the ions that gain electrons, and these are the monoatomic ions that lose electrons. Okay? That's all you got to know about it right now. It's just like, know the pattern, don't really have to understand a lot about the reason yet. Okay? Hopefully it'll make more sense when we get to that point. All right, we ready to go to the next one? So this next pattern we're going to look at has to do with the way electrons behave in bonding. Actually, there's 3 patterns we're going to look at that have to do with this. Okay? We looked at, I explained that when you put metals and nonmetals together, and we're looking at the dividing line between metals and nonmetals, I explained that metals tend to give up electrons to nonmetals, okay? And that nonmetals tend to share electrons with other nonmetals in a covalent bond. Well, this illustration, this little cartoon is kind of hopefully making it a little bit, helping you to understand a little about what's going on with the next 3 patterns, okay? That top section there is illustrating what happens when 2 different nonmetal atoms are sharing electrons, because they don't share evenly, okay? So when you think about sharing things, you know, it's like, yeah, I'll give you my turkey sandwich if you give me your peanut butter sandwich. You kind of share evenly, right? You know, everybody gives and gets something. But between 2 nonmetal atoms, that sharing doesn't happen evenly unless they're the same atom. So, for example, oxygen bonds with oxygen to make O2. That's the oxygen we breathe in the air. Well, that's an even sharing of electrons. But if you put carbon and oxygen together, well, carbon and oxygen don't share evenly, okay? Or hydrogen and oxygen, they don't share evenly. And so that top section there is kind of showing how the more electronegative element in this case on the right, the blue one there, he's stronger. He's pulling on those electrons more strongly than the less electronegative element on the left. And so the electrons are spending more of their time over here where the blue element is, atom B over there in that top gray section, okay? And the result is that side of the bond is more negative, electronegative, okay? Because those negative electrons, there's more negative electrons on the right side than the left side, okay? And that brings us to what electronegativity is, okay? It's called electronegative because when you move more electrons to one side of the bond than the other, that side of the bond is more negative because electrons are negative. Does that make sense? Anybody confused? You got it? You confused? All right. You understand that electrons are negative, negatively charged. If you put more electrons on the B side than the A side, that side's going to be more negative because there are more electrons. That make sense? Okay. Did I simplify it enough? That good?
So that makes it stronger.
No, the pull is stronger. The result is the negative. Okay? Because the blue atom here in that top gray section pulls more strongly on those electrons, that means the electrons are over on that blue side, and that side becomes more negative because the electrons are there. That make sense? Okay. So we have a pattern of electronegativity on the periodic table. All right, so we're going to look at pattern of electronegativity, or just let's just call it electronegativity. So the electro part is from the electron. The negativity has to do with the charge. Okay? That makes sense? So let's define electronegativity then. I'll zoom this in just a little more. The electronegativity. This refers to how strongly one atom pulls on the electrons it shares with another atom. And this is happening in a covalent bond. Doesn't happen in ionic bonds because in ionic bonds the electrons are completely moved from one place to the other. This is just the sharing part. Okay? It refers to how strongly one atom pulls on the electrons it shares with another atom. Now we're going to see why it is that noble gases are called noble gases, and they're called. The big picture is that they don't bond with anything. There's no reason for them to bond. They got all the electrons they want. So these atoms over here on the right hand side, they don't have any electronegativity in this column right here, starting with helium, going on down to really radon, I suppose, or xenon, okay? Those elements don't bond with anything because they don't have any reason to gain or lose or share electrons. So they don't have electronegativity. We're going to leave that out of our pattern here. These noble gases, we're going to say, have no electronegativity. Okay?
Why did you say they have no electronegativity?
They don't bond. You can't have electronegativity if you don't bond, because bonding, the electronegativity results from sharing electrons unevenly.
Is that because they have 8?
Yes, exactly.
I thought
Okay.
it was just like,
Yeah, that's exactly right. Sounds like you had you got a lot out of your physical science class. Good for you. Okay. All right, so the most electronegative element is fluorine. That might seem kind of strange. It's a small little atom, but it's the most electronegative. It's the one that pulls on electrons the most strongly. Okay? The least electronegative element is francium. Okay? So the pattern of electronegativity, and it pretty much is smooth along here. There's some bumps in the road in this section in the middle here. But for the most part, it's pretty smooth. Okay, we got the highest electronegativity up there on the upper right, the lowest down here on the lower left. So this is the highest up here, and the lowest down here. Okay? Okay, so back to our cartoon. The next pattern we're going to look at has to do with electrons being completely moved from one place to the other. Now that's the way we think about it. That might not be the reality of how you get more electrons on one atom than another. But if you look on the right here in the bottom section, the white section down at the bottom, the blue atom over here is kind of one. Okay, and so it's got both electrons over there. All right. And then on the left side, that would be an atom that has lost those two electrons, all right? Or it might have lost one. But in any event, the electrons have been completely moved from the purple to the blue, okay? As a result, then, the blue atom over here has a completely positive charge. It is not a partially positive charge from sharing the atoms the electrons unevenly, as it does in that gray section on the top. It's completely moved from one place to the other. So an electron has a negative charge, and for every electron added to the blue atom over here, it would have completely gotten a complete charge. All right, we'll talk about that. Those are monoatomic ions now. So then in this illustration, the purple element over on the left side would be the metal, and the blue one would be a non-metal. Okay. Not 100%, but close to it, that would happen, all right? All right, then let's take a look then, and there's two patterns we're going to look at here. And one of these patterns is, well, if I get my computer to work here, is called ionization energy. Okay, so the pattern we're going to look at is actually first ionization energy, but we're going to define ionization energy over here. Okay, so ionization energy is the energy that must be put into an atom to remove an electron or electrons. Okay? The energy that must be put into an atom to remove electrons. Okay? First ionization energy is going to be just what we're talking about, the pattern for removing one electron. First ionization energy, first electron. Okay, sometimes you can move more than one, but whatever. All right, so the element or atom that's the hardest to remove an electron, so it requires more energy to remove an electron, is helium. Okay, that's the hardest one to remove an electron. And the one that's the easiest to remove an electron is still francium. Okay? And so the pattern we're looking at is from the highest over here with helium to the lowest over here with francium. Okay. It's easiest to remove electrons from metals. It's really hard to remove them from nonmetals. They want to gain electrons, which is the next pattern we're going to look at. All right, so the opposite effect, if it takes energy to, you have to put energy into an atom to remove electrons, then when you put extra electrons on there, the opposite effect is you get energy out. Okay? And that's called electron affinity. Okay, so this is the energy that is, the word is emitted, or let's say, suppose we put it out, let's say taken out. Of an atom. When extra electrons are added. Okay? All right, so again, we're going to talk about just the first electron we put on there. So first electron affinity. Okay. Well, remember what we said about electronegativity? That these atoms over here don't need to bond, they don't need extra electrons, they don't need to share or anything like that? Well, for the same reason then, those noble gases over there have no electron affinity because they don't need any extra electrons. They don't want any electrons. They don't give away any energy when you put it on there. Okay? So once again, we're going to leave the noble gases out. No electron affinity. Okay?
Can you go back to the definition, please?
The energy that's emitted or taken out of an atom when extra electrons are added. That's what the definition is. Okay? So the atom then that pulls on electrons the most strongly in electronegativity is also the atom that gives away the most energy when an electron is added, for the same reason. So fluorine then is our atom that has the highest electron affinity, gives away the most energy, and francium gives away the least energy. Okay? So we still got that same sort of pattern here. The pattern is the same as electronegativity. Okay? But the difference with first ionization energy is you don't include the noble gases. So the highest electron affinity is over here, and the lowest electron affinity is down here. Okay? All right. Oh, draw my pen. Okay, here we go. Reactivity. Now, it's hard to define reactivity. And when one person defines reactivity in one way, you get a different pattern than when another person defines reactivity in a different way. after looking at the different definitions and trying to understand where these arguments are all coming from, what I'm going to give you, I think, is probably the most accepted way of thinking about it, okay? So if you'll look on your periodic table and find platinum and gold, or for that matter, silver, platinum, and gold, okay? Well, where do you find a lot of silver, platinum, and gold?
In the ground.
Huh?
It's in the middle.
Yeah, where do you find a lot of silver, platinum, and gold?
Like, actually, like, find it?
Yeah,
Like, in the ground?
Probably jewelry.
jewelry store.
Oh.
Okay, you said it? I didn't hear you say it, I'm sorry. Okay. So the reason that, and those are called precious metals, silver, platinum, and gold. The reason they're called precious metals is that they don't corrode. Anybody had to clean the silver at home? No?
What?
Yeah, but
Clean the silver?
Clean the
you
dishes?
just like, never
The
mind.
forks?
Go ahead, tell
It's
me.
just like a spray, isn't there?
Well, there is a spray, and there's some silver, there's a paste to use that you rub it and stuff like that. The thing is, it's, iron, when it corrodes, it makes rust. It combines with oxygen in the air. Copper, when it corrodes, this is copper, it combines with oxygen in the air, makes a green stuff, okay? Oxygen makes an orange looking stuff, that's regular rust. Silver, when it corrodes, it does so very, very slightly, but it doesn't even react with oxygen, it reacts with sulfur. There's no sulfur in the air, it won't react at all. Gold won't react, it's really hard to get gold to react with anything, okay? Platinum doesn't react, so they're called precious metals because they don't react. So if you understand why we have platinum and gold in the jewelry store, you'll understand why these are the least reactive elements, okay? Now the gold you buy in the jewelry store is not pure gold, all right? It's an alloy mixed with some other metal because pure gold is really soft. You ever seen any old movies like old westerns or pirate movies where they bite down on the gold piece? The reason they bite down on the gold piece is if it's not pure gold, if it's pure gold, you can put an indentation in it with your teeth. So they test it to see if it's pure gold by biting on it, okay? So anyway, those are the least reactive elements. So we can go ahead and put that in here in terms of our reactivity chart. Find about where you think they are, right in this area here. There's gold, and there's platinum. Okay? These are the least reactive elements, okay? Chlorine is one of the most reactive elements, okay? But the reason it reacts is different from the reason that potassium and sodium over here react, okay? All right? So these are both regions of really high reactivity, okay, on the right and left sides. Now this whole column over here is pretty reactive, on both right and left sides. Both the right and left columns here, this halogens column, we'll talk about that in a second, and this alkali metals column, we'll talk about that in a second. Those are all pretty highly reactive, but out of all of those, these are the most reactive of all, okay? So most reactive is this column and this column. Most reactive of all is this section and this section, and least reactive is right here, okay? And so you get a kind of pattern like this. So higher going this way, lower going this way, higher going this way, lower going this way. Okay? we could say that highly reactive elements are those that react with the most violence. How about that? That might be one way to think about it. And that's not really a very good definition either, because it really doesn't explain how fluorine does what it does, for example. But we're not going to get too deeply into some of those things, okay?
What does fluorine do?
Well, let's don't go there right now, okay? Let's just don't worry about fluorine, just to take my word for it. It's the most reactive, but doesn't react in a way that produces as much violence as chlorine does. Not nearly as much because of its structure, okay? And depending on how you define violence, some of the elements in this column over here might be more reactive as you go down, even more than potassium and sodium, but again, it depends on how you're defining all that, okay?
Can you go back over?
Over here. All right. We ready now? Okay, last one. Okay, special groups. So we have some regions of the periodic table that have special names. Okay. Let me explain this first, just to be clear about it. All the elements in the same column. Remember what columns are? If you're standing up, that's a column. If you're laying down, that's a row. All the elements in the same column, that's called a family or a group. All the elements in the same row, that's called a period. Okay? So this is, for the most part, all of that first family. All right? It doesn't include hydrogen, but this has a special name, and it's called the alkali metals. Alkali metals. Okay? And this next column, the entire family or group here, this is called the alkaline earth metals. Alkaline earth metals. We've already defined the last column on the right. What are they called? Noble gases. Okay. Right next door to the noble gases are the halogens. Okay. And all these columns over here have special names. We're not going to worry about those names, okay? We're only going to worry about the last two and the first two and some other stuff we're going to talk about in a minute. These other columns over here in the nonmetals, let's see, fluorine, oxygen, nitrogen, carbon. Yeah, I got it right. Here we go. We'll name these columns right here by the element at the top of the column. Okay, just to make it easy. They do have names. We won't worry about it. Okay, we'll just call this the oxygen family. and the nitrogen family. And the carbon family. And the boron family. No, that's a boron family, right. I saw some people look up at me and say, what? Okay, boron. Boron. Okay. All right. So those are special groups. While on this region arrangement here, let's also make sure we're clear that these are called transition metals. And these down here are called inner transition metals. So if you will look at your periodic table, the periodic table I give this class, and look down here where the inner transition metals begin, okay? And look at where these arrows come from. Here's cesium, barium, lanthanum, 55, 56, 57, but that's not 58. 58's down here. And so you go from 58 all the way over to lutetium 71 before you then get to hafnium. So this whole section down here, and the same thing happens with the next row. This is 88, 89. Here's 90 down here. And you go all the way over to the right, and then you come back up here to rutherfordium. Okay? This whole section at the bottom actually belongs right in here. Now we ought to take a pair of scissors and cut this out right here, just like that, and slide all this over and stick this whole section down right up in there. But if we did that, it wouldn't fit on a nice 8.5 by 11 sheet of paper. So the reason that inner transition metal section is down there is because it doesn't fit on an 8.5 by 11 sheet of paper like that.
Is that why it's called inner transition?
Because it fits inside the transition metals.
Is that really
It fits
the only reason?
pretty much.
Wow.
Yes.
And what are transition metals?
Well, let's don't worry about a definition because it transitions between valence level regions. So remember when we did S and P sublevel regions? This was the S sublevel region over here. This is the P sublevel region. This is the D sublevel region. It transitions between them. Okay? And I think we did we do S, P, D, and F sublevel regions? Yeah, we did that. So the S and P sublevel regions, S and P orbitals and electrons are the valence level. S and P electrons are the valence level. Those are the ones that most govern how it is that atoms bond. Okay? Most govern how atoms bond. All right? Now, before we quit, I need everybody's attention. Starting tomorrow, we'll start explaining how to do orbital notation and then electron configurations. And once I explain orbital notation and electron configurations, what's due 2 days later? Your project. Okay?
Like Saturday?
Monday. You're not coming in on Saturday. What difference does it make? Doesn't make any difference if it's due on Saturday. Okay?
Making sure that you were
Got
gonna
it.
make us, like,
Okay?
submit, like, the-
So if you want to know the deadline, if you want a deadline, okay, we are getting really close. So I would listen, please listen, listen for the Element Q project. All right. You can go ahead and plan for it being due on Monday. Now, that means I haven't assigned any special homework for you tonight, right? I expect you to get all of your research about your elements done tonight. Get it finished tonight.
That's our homework.
That's your homework. That way,
We gotta do all of it.
well, I've been asking you to work on it along. So listen,
That was yesterday.
stop, be quiet and listen. Be quiet, be still. Listen. Get all of your research, the interesting stuff about your elements done by tonight. Okay? Work work on electron configurations and orbital notation over the next couple days. So that way you don't get bound up trying to get all this stuff done. You've got basically a night where I haven't assigned any other homework for you to finish up your research on your element cube, okay? I will show you how to do the orbital notation electron configurations for your element cubes. Then on the weekend, you're going to have to print out your element cubes, cut them out, and glue them into a cube. Okay? Now Monday, if they're due on Monday, and that doesn't change, let's assume it won't change. On Monday then, you're going to bring your cube in. I would recommend, since this is fourth period, that you bring it in and drop it off here before school. That way you're not taking it around all day long and worry about it getting crushed. Got it? But you have to glue your cube up before you come to school. Do not bring in a cube with wet glue on it. Got that? You got the whole weekend to work on it. All right? You can do this. Any questions?
No, the research doesn't need to be on anything specific, right?
Well, it needs to be about stuff that would make it interesting about your element. That's what your research, so far, that's what your research is going to be. You got 4 blocks to fill with interesting stuff.